Lovely. Well, welcome back, everyone. And this is a session that I know everyone in the audience will have been looking forward to. We're talking about the quantum computing commercialization path, and we have updates from 6 leading players around their roadmaps and stacks. And it's a range of providers across a range of different technologies, from innovative startups through to established players. So, to begin with, I'd like to introduce Mandy Birch from Rigetti. She's the Senior Vice President of Technology Partnerships, and she leads business development and delivery for multi-sector collaborations, including a DARPA quantum program and a public-private consortium to deliver the first commercial quantum computer in the UK. She's also on the core leadership team of the Department of Energy National Quantum Initiative Centre, where she serves as the ecosystem development lead. So, Mandy, if you could take over and share your screen with us. Thank you.
Excellent. Thank you. It's great to be with you all today. Let me get my screen share going here. And in thinking about the path to commercializing quantum computers, let's journey back to 1951 and the commercialization path for general purpose digital computers. Most people agree that the world's first commercially available general purpose digital computer was the Ferranti Mark I, also known as the Manchester Electronic Computer, that was delivered to the Victoria University of Manchester in February of 1951. And about a decade after Alan Turing's work at Bletchley Park. And soon after that, the UNIVAC was sold to the US Census Bureau and shortly thereafter the US Air Force. And in that same year, 1951, after a 4-year journey, the J. Lyons and Company, a British catering company famous for its tea shops, but with a very strong interest in new office management techniques, decided to take an active role in promoting the commercial development of computers. And they were able to integrate a computer after this 4-year journey into their weekly operation of bakery valuations and how to schedule their jobs. So as we look at this path to digital computing, it's interesting to look at this pattern of government having the first applications, then seeing the research community adopt the computing capability about a decade later, and simultaneously industry adopting the capability. So I think that there is a general pattern here that we can see emerging that looks similar in quantum computing as well. And I would say that the common thread among these is that this pursuit of advantage, useful utility of quantum computers is the path to commercialization. And there's really 3 elements I'd like to talk about today that are part of that path. And first is having the performant hardware underpinning the capability, ensuring accessibility to the systems, and then working on real world problems. And I'll address all 3 of those in our talk today. So I'm Mandy Birch. I'm the Senior Vice President of Technology Partnerships at Rigetti Computing. And by way of introduction to Rigetti, we are a full stack quantum computing company with hardware at our core. So we own and operate the world's first dedicated quantum integrated circuit foundry, which you see on the left of the slide here, which enables our rapid R&D cycles and reliable production processes for manufacturing our chips that then get integrated into the cryogenic environment and the rest of the stack on top of that. So on the right here, you see our quantum compute facility at our headquarters in Berkeley, California. And this is where we not only do our research and development, but we make our latest and greatest quantum systems available to you over the cloud. And to look at the evolution of our quantum cloud services, we're currently on the 3rd generation. We put our first quantum computers on the cloud back in 2017 and launched our quantum cloud services platform. And with every system generation, not only did we improve our quantum processors, we've really focused on pioneering this hybrid infrastructure that tightly couples the quantum capability and the classical resources to enable the highest possible performance out of the systems that we have today. And so today we support ultra low latency connectivity that's less than 1 millisecond millisecond between a customer's high performance classical hardware and Rigetti's quantum processing units, which are, it's an essential capability to have this hybrid setup for our near-term variational algorithms. So when we first put our systems on the cloud, you connected directly with your laptop or your desktop computer to the QPU. Then we moved to having an environment where you had the classical and quantum capability here in Berkeley co-located, and now users can leverage their high performance classical capability to connect directly to our systems with low latency. And at any time you're interested, you can check our website to see what our current systems that are deployed are. Right now, we have our Aspen 9 device deployed. It's part of our Aspen series. It's our 32 qubit node technology. You can see that our single gate fidelities are above 99% today, and we have our 2 qubit gate fidelities in the 95 to 97% range. And these systems are available essentially in 3 different ways. One, you can access directly through our quantum cloud services, and we work with a select number of partnerships that I'll talk about a little bit later in the presentation to offer that capability. You can access our systems through our partnership with AWS and the Braquette service. And then the third way you can access our systems, if you are interested in publishing what you do on our machines, you can work through Oak Ridge National Lab through their Quantum Computing User Program. I wanted to share just a little bit about the journey. As I said, the path to commercialization is looking for quantum advantage, but we also have in view this path to fault-tolerant quantum computers, which is essential for the later stages of commercialization. So just to share the journey that we've been on and where we're going, our single qubit devices became available only really to researchers and hobbyists. And then when we were able to deploy our devices on the cloud and introduce our cloud services in the 2017 and 2018 timeframe, this opened up accessibility to a broader group of folks, application developers, and quantum capable corporate and institutional users. And then in 2019, through our partnerships with AWS and Oak Ridge National Lab, we were really able to open up our systems to a much larger community, particularly the machine learning developers who have a fundamental capability in the computing languages that are natural to quantum computing. And so here we are where we've developed these noisy intermediate scale quantum systems that are available. And right now we're focused on the quest for quantum supremacy and possibly quantum advantage. And I wanted to share how we're thinking about these different ideas of quantum supremacy and quantum advantage. So quantum supremacy and the landmark achievement from Google is about being able to perform an abstract task that's impossible on a classical computer. And we think about weak quantum advantage, which we think will be one of the next inflection points that we hit over and over again with different applications, is the capability to solve a practical, operationally relevant problem better, faster, or cheaper than a classical computer can do. However, this may not be durable. So in other words, there's no theoretical complexity argument underpinning it, and the advances in classical computing may well overtake a weak quantum advantage milestone. So really the most significant milestone will be the strong quantum advantage, where you combine this weak quantum advantage, you're solving a practical problem better, faster, or cheaper than you can with classical computing, with this theoretical complexity argument that's inherent to quantum supremacy. And you'll have a enduring advantage once we hit that point. And then it's a matter of continuing to work on error correction, in particular, to be able to have the first small scale fault tolerant computers, and then the practical larger fault tolerant computers that are much larger on the time frame. But all this to say, this pursuit of quantum advantage is critical and is on the pathway to commercialization and to the larger fault tolerant quantum computing goal. And then back to what I said at the beginning, there's really these three elements that are critical to pursuing quantum advantage. One is developing the horsepower, the underlying capability of our systems, being able to have more qubits, to be able to increase the fidelities and overall have higher performing systems. And to be able to really get the most out of these systems have to be accessible to a broader group of people. So that's what we've worked on in the last couple of years, is making these accessible over the last 4 years, first through our quantum cloud services and now through our partners to get a broader range of folks able to work on the systems and make progress. And then to work on co-development with us essentially and get feedback that's driven all the way down to the manufacturing capability that we have. And then finally, an essential element is just working on real world problems and having a framework to advance both the algorithms and then optimizing the underlying systems in this NISQ era to be able to solve those problems, those specific challenges and specific workflows for practical problems. And it's quite clear that one of the biggest challenges right now is being able to mitigate errors and then also be able to provide the benchmarks to show marked progress against classical computing capability. So these three elements, underpinning capability, making the systems accessible, and having a framework to work on practical problems are essential to this pathway for commercialization. And a big topic of discussion for today is scaling up the number of qubits in a quantum computer. So we could, in theory, today manufacture a 500 qubit chip. But it really wouldn't be very useful. So a 32 qubit chip like our Aspen node that we have deployed today has hundreds of components that have to be manufactured with high precision. So even if the component failure rate is low, a successful quantum device is the product of hundreds of 99% success rates. And that 99% success rate sounds good, but when you aggregate that, that gets pretty low. So if you're trying to do 100 qubits and that's the only thing you have to manufacture well at 99%, you multiply 99% by 100 and you've come out with a 36% probability of getting a good device. So those add up pretty quickly and make the probability of manufacturing something of high quality at scale very difficult. So in addition to that, as you manufacture larger chips, larger devices, more scale, as we scale up, we can only fit a fewer number of chips on a silicon wafer, which means that we have fewer chances to get it right. So all of this to say that there's a lot of demand on the underpinning manufacturing to be able to scale this. But we have a trick for breaking this exponential scaling problem, and that's to build our quantum processing units in a modular way. We can place a 4 Aspen scale chips onto a single carrier chip that you see here right next to each other. And on that carrier chip, then we can connect the qubits at the edge to each other and mediate a quantum entangling interaction. So what does all this mean? It means we only have to get good at making lots of identical smaller chips. And there are actually a whole host of other engineering challenges to scaling quantum systems. And hopefully you'll be able to attend the session after this where my colleague Mark Field will discuss that in more technical depth at that panel. Okay, so on the last slide you saw that diagram. Here's actually a picture, an image of an early modular QPU device. Today, we have the hardware capacity to host modular QPUs, roughly equivalent to 4 Aspen class chips. So that's around 150 qubits. We recently shared early research results demonstrating 99% fidelity entangling gates across physically separated die, confirming that this approach to scaling doesn't come at the price of performance. And we're excited to deliver our first modular QPUs via QCS later this year. Of course, having the best quantum computers in the world means nothing without knowing what problems we can solve with them. At Rigetti, we engage in multi-year, multi-sector partnerships to co-design and develop novel solutions from device architectures and infrastructure to applications and software optimizations, all driven by a customer's need to solve a real problem. And I'd like to highlight 3 of the partnerships that we have today. First is our DARPA program for optimization with noisy intermediate scale quantum devices in partnership with NASA and University Space Research Association. And we're developing the full stack here to be able to solve a complex scheduling problem. We've had some innovations through this program. We're working on different gates. You may have seen our publication back in November where we published our XY native gates that helped us make a significant advance in this work that we're doing with DARPA. A second partnership I'd like to highlight is the Superconducting Quantum Materials Systems Center at Fermilab, where we're partnering with 80 different principal investigators to fundamentally advance the coherence time of our devices. We're working on deploying integrated 2-dimensional our superconducting qubits with these 3-dimensional superconducting RF cavity qubits that have a much longer coherence time for some near-term applications in high energy and condensed matter physics. And then finally, I'd like to highlight our Innovate UK program, where we are deploying the first full stack quantum computing platform in the UK. We're working in partnership with Oxford Instruments, who has developed the fridges and hosting capability. We're working on specific quantum applications in quantum simulation with phasecraft and with quantum verification and quantum machine learning with the University of Edinburgh and Standard Chartered, and really with the pursuit of quantum advantage in mind. And I've reached the end of the time so quickly here, so I would like to invite you to connect with us in the conference. You can use this QR code, and we'd love to hear from you. Thank you.
Thank you so much, Mandy. That was fantastic, and well done for getting through it in the time. If I could invite Richard to, if you could start up your camera and slide share, I'll introduce you. Next up is Richard Moulds, who's the General Manager of Amazon Bracket, the quantum computing service of AWS, where he's responsible for the strategic, commercial, and operational management of the service. Prior to joining AWS 3 years ago, Richard was the GM of Whitewood Security, a quantum networking startup. And before his work in quantum, he spent more than a decade building products and services in the InfoSec market, primarily focusing on cryptography and data protection. Richard, all yours.
Thanks, Amit. It's great to be here. Thanks for the invitation. It's a thorny topic, commercialization. I was thinking that there might be divided opinions on this across the community. You know, there's lots of people, even inside my own organization, that think it's way too early to talk about commercializing quantum computing, where of course there are others that are moving fast, maybe even too fast, to try to convince everybody that this is useful now, that we can solve big time commercial problems now. We still have a long way to go, obviously. But at the same time, solving commercialization problems is not easy. Fixing pricing and support, the overall customer experience are things that will take a while. So we should get started. So in thinking about the title, this notion of a path towards commercialization, I got inspired by this image, the notion of innovation trail. At Amazon, we're all about innovation. So what does commercialization really mean? It means something different probably to most people that are listening here. But to me, it really means that we're finding a path to a meaningful outcome for customers. That means we have a sustainable value proposition as an industry, and effectively it means that quantum computing can finally become a business. Whether that's 5 years away, 10 years away, who knows, even longer. But it's a very fine line to get there. We have to tread extremely carefully. This is a perilous journey, as the diagram shows. If we lose sight of the fact that we're heading towards a customer goal and we forget about the needs to create a sustainable business, then we're going to get sucked into either of the pitfalls on the left-hand side or the right-hand side. We could be tempted into the valley of perpetual science experiments. We never really quite get to an answer. We never really make it real. We never really find a way to bring in the broader community, and it stays a cottage industry. That's not good for anybody. Perhaps even worse, we tumble into the chasm of corporate marketing, where we're not really focused on commercializing quantum computing at all. we're really focused on making commercials to commercialize something else. We're focused on creating a sheen of innovation, or we're trying to, give some impression that, the company's going somewhere where it's not really. So 2 things to really avoid, I think. Let's stay focused on some sense of an end game, some sense of purpose. What is in this for customers? Customers are not interested in hype. Customers really, in the most cases, are not interested in research. They're interested in actually solving problems. So we're trying to envisage what that world would look like at some point in the future. Envisage the notion of a production scale quantum computing experience. So how do we get there? So at Amazon, as I'm sure many of you know, we believe deeply in the notion of innovation flywheel. We've seen it work lots and lots of times, whether we're talking about IoT, AWS as a whole, robotics, machine learning, and hopefully now quantum computing. So I'm reliably told that this is an original sketch from the napkin that was the original thinking behind Amazon.com. And the notion is that we can accelerate growth through a self-reinforcing notion of a customer experience. The growth comes fundamentally from a better customer experience. Lots of components to that, in this case, of course, of online shopping. Traffic attracts sellers, sellers create selection, and selection creates an experience. But growth in itself enables other side benefits, such as lower prices from a lower cost base, which ultimately amplifies the customer experience to generally speed up the flywheel. And I think we can apply the same approach to quantum computing. So we still focus on the customer experience on the right-hand side. We all know that what's holding this industry back right now is the quality of the hardware. We want hardware that can deliver meaningful results. We can generate a customer experience. We can create innovation around applications and use cases, which will drive innovation and investment in the industry, which will lead to machines that can finally get us there. We think that generates growth across the industry, and we think that that growth will stimulate the emergence of an ecosystem, developing tools, and ultimately developing an even richer customer experience, generally revving up the flywheel. But I think there's a couple of observations that we need to make. Everybody needs to be on the same flywheel. I think it's been the case for a long time in this industry that folks are experiencing quantum computing in different ways: free services, paid services, private access, subscription models. People are on different flywheels, and those flywheels are running at different speeds. It's important we literally get on the same flywheel. We live the same life, we build the same tools, and we have the same experiences. That way we can innovate as an industry, I think, faster. It's also important to think that this innovation flywheel, albeit interesting to us as the industry of quantum computing, isn't necessarily how customers think about their life. They don't care necessarily whether the quantum computing industry takes off or not. What they care about is there a path to solving real world problems for them? This, in a sense, can be a rather myopic view that we might have, is that there's just a flywheel just for quantum computing. Customers don't really care. If we can solve their problems with classical technologies, then that's perfectly okay to them. What's interesting in the flywheel is, every different aspect of the flywheel, there are different communities serve different aspects. Whether you're a hardware provider, whether you're a consultant, whether you're an educator, whether you're a software company developing tools or algorithms, you can see hopefully where your role is on this flywheel, and hopefully everybody that's listening to this call now can get a sense of how they could contribute with your unique skills. So we think this is the way to move forward. We think this can bring the community together, and we think this can accelerate the path towards a commercial production, meaningful service. So what are we doing at AWS? I'll just give you a brief introduction. So my main focus is on the left. Bracket is our commercial service, quantum computing. We launched it in the middle of last year. And in fact, if you want more information about the service and some insight as to how we can apply some of our newer releases, such as machine learning, there's a session tomorrow given by my colleague, Eric Kessler. On the right-hand side is our research center, which we announced a year and a half or so ago. It's based on the Caltech campus in Southern California. It's focused on hardware and software developments. If you're interested in digging deep into some of the research topics that they're focused on, in fact, just yesterday they posted a blog post about some innovative work they've done in the area of error correction. So check out the Quantum blog. I'll give you a link to it later in my final slide. In the middle is our go-to-market area. So the Quantum Solutions Lab is our professional services team, consultants that take customers through in a collaborative process to explore different use cases and to try and solve specific problems. And again, try to bring together the worlds of classical computing and quantum computing. So fundamentally, what we're trying to envisage here is a production quantum computing platform, not just a showcase for individual technologies. I apologize for the slightly literal slide. So at the bottom, we've got lots of cool technologies, lots of cool hardware. We'll talk about those in a moment, and some interesting tools. But that doesn't constitute a great customer experience necessarily. We want to build a platform that works for customers. Customers have told us, over more than a decade now, what constitutes a great platform for classical compute and the services that run on it within AWS. And if we can apply some of those same rules to quantum computing, we're literally not starting from scratch here. So if you think of some of the supporting columns behind a great customer experience, think about operations. Customers expect stuff to work, as they think it will. Okay, that's not easy in quantum computing. This is early stage technology, limited capacity, limited availability, but nonetheless, we have simulators. Some things can be 24/7. We are striving to make the world of quantum computing, early as it is, feel like a professional, available, and ultimately scalable service. Security is another really important point. I think the industry still hasn't really grappled with the need for security. The hardware is getting exponentially faster, more powerful. That means that the value of the data is going to be getting exponentially more valuable as well. That happens real quick. Security does not happen real quick, right? Security takes a while to evolve. Security takes a long time to prove and maintain. So focused on security now, how do we protect data, both in the classical domain and the quantum domain, is something we're very much focused on. It's a huge issue for AWS, and we think it's going to be important for quantum services on AWS. Integrated access within a broader cloud platform is also very, very important. Customers have, particularly large customers, have distinct policies about managing access, auditing use, tracking billing, storing data, accessing classical systems and classical compute, arranging for hybrid systems. These are all massively complicated topics, and it's fundamental that quantum computing isn't seen to live in a silo. It's part of a broad experience, it's part of a broad cloud platform, and it should be subject to the benefit of all of the other services and all the other capabilities and management tools that exist within that platform. Fourthly, technical support. It's incredibly important that customers pick up the phone and get some help. It's what has enabled cloud computing to be so successful. And there's no reason why quantum computing should be any different. The Bracket service is supported by the mainstream premium support team that supports all the rest of AWS, obviously with their own subject matter expertise. The commercial model, pricing. Okay, so this is an area where we think there still needs to be a lot of innovation in this market. Pricing is all over the map in this industry right now. There's no agreement on how you should charge for access to these resources. How valuable are they? How much are customers willing to pay? Really, what is it worth to access quantum devices? And how will that change over time as the devices get more powerful? So trying to agree on the pricing rates and the pricing dimensions for accessing quantum machines, is something that's going to be very much an evolving topic over the next 5 years or so. We literally are starting from scratch. We tried to put a stake in the ground. We defined a pricing model for Bracket, which normalizes pricing, or at least pricing dimensions, across all of the hardware that we provide. We charge by tasks and we charge by shots. We're trying to bias towards more complex workloads. We're trying to encourage customers to push the limits of the hardware, innovate more quickly. Finally, marketing platform. Clearly it's important that we can get the message out, not just from an Amazon perspective, but from the perspective of all of our partners, the solution providers that build on the service, and the hardware providers that use the service as a way to access their customers. So we think about commercialization. It's something that applies to the whole community. It's not just something that applies to us. So who is this platform, this quantum computing platform that we call Amazon Bracket? Who's it for? Lots of different constituencies with different goals and different requirements. The whole point about a platform is that it helps avoid doing the things that you don't want to do. Sometimes you'll hear us talk about undifferentiated heavy lifting at AWS. The cloud is all about trying to prevent folks from having to do the stuff that is boring, the stuff that takes up their time, the stuff that prevents them from innovating in the areas where they can do best. So the quantum computing platform, as we see it, is a way to save some of that heavy lifting and a way to double down on some of the aspects that customers believe to be the most valuable. So we think about here, obviously, the quantum hardware providers are the bedrock of our service. We're thrilled that D-Wave and IonQ and Rigetti were brave enough, frankly, to embark on this journey with us as our launch partners. We're certainly working hard to add more hardware to the service to give even a richer and broader example of the different types of quantum technologies that you can use to run both gate-based systems and non-gate-based systems. We think it's important from their perspective that they don't have to build necessarily a commercial front end. If you're a group of physicists, you're a spin out from a university, you're in a lab somewhere, building a commercial front end to your system, supporting your customers, building all the tooling, running an operational service, believe me, is not that easy. It's nice to be able to hand that over, I think, to us. And as I say, it helps, hopefully, our hardware partners to simply move faster and do the things that they do best. In terms of building on the service, we have partners that are either building on Bracket to build their own solutions in the corporate sense, they're building their own business in the context of our solution providers, or they're researching on Bracket, or they're educating on Bracket. I've tried to indicate some tooling here. As I said, this is a road that AWS has been down a number of times before. We have great support services, the Quantum Solutions Lab. There's a link there in the top left-hand box. We have a tremendous amount of support for startups, activating their use in the cloud, getting them started, providing them credits to give them a bit of a jump. Services called Activate. There's a link there in the second from left box. And researchers. We recognize that researchers, have some pretty complicated workloads. They want to do weird stuff, and that's okay. They want to push the edges. Get in touch with us. There's a program to request research credits from AWS. You can apply those credits directly to Bracket. We can fund your research activities. We can hopefully enable you to innovate and further the cause of this industry. Before I finish, I wanted to give a call out to some of our solution providers that literally have built a business or are building a business on the Bracket service. We hope the value proposition to them is that it avoids the need for them to make piecemeal deals across the industry and try and stitch together essentially a back-end fabric. Our goal is to give an easy to use, comprehensive, straightforward, predictable, operationally meaningful and secure service for them to use as their back-end, for them to focus on applications, use cases, specific industry verticals, chemistry, optimization, whatever it might be. It's important that they can showcase their skills and their value add to their customers, and it's important that they get there quicker. I specifically wanted to call out QCI, Quantum Computing Inc. Today, they just announced that their Catalyst service, which is an optimization service, runs on Bracket. What's really interesting is that it's not quantum computing specific. Okay, their name is Quantum Computing Inc., but their service is not specific. If they can solve problems, optimization problems classically, or in hybrid with quantum computing, or solely with quantum computing, then they'll do that. I think is a great example of how we perhaps avoid some of the myopia around being a quantum computing industry, and we think broadly how quantum can play in the context of a broader classical environment. I want to give a huge thanks to all of our partners. They really help this service grow. We get a tremendous amount of feedback and amazing creative thinking from our partners. So I call out to folks that aren't on the service. If you're a solution provider, if you're a hardware provider, come talk to us. We have a virtual booth throughout the show, and various folks from the Bracket team are on that booth. Please come try our service. Here's a link to the service itself. Easy to get started, pay as you go, on demand, no upfront commitment. Just go try it. If you're interested in our research activities and also the opinions of some of our partners, we just launched a quantum specific blog channel. Here's a link to it. If you want to hear more about the bracket service specifically, there's a session tomorrow afternoon, 3:20 p.m. Eastern. Eric Kessler, one of the senior product managers on the service, is giving a run through about some of the work we're doing around quantum machine learning. And if you're interested in a career at AWS, here's a job posting page which lists, I think, more than 50 jobs in the quantum computing initiative across AWS. So with that, I'll say thank you and hand it back to Amit. Thanks, Amit.
Thank you very much, Richard. Wonderful overview. Moving on, we will have Bob Sutor. Bob, if I could ask you to activate your
Sure.
camera. Fantastic.
Let me just, all right, and let me share.
And Bob, as many of you will know, is the chief quantum exponent and evangelist for IBM's quantum computing service. He translates the science and evolution of this highly technical area so it can be understood and used by business people, industry analysts, educators, government decision makers, and the media. Pleasure to have you, Bob.
Pleasure to be here. Let me just verify you can see my screen.
Yes, all good.
Okay, very good. First, Mandy, I apologize. I didn't realize I had my video on. I was listening intently. So let me kick this off. First of all, by the very nature of this talk, I think everyone here, as well as other people who are providing, absolutely are after providing extraordinary customer solutions via quantum. We're not doing quantum for science sake. These are commercial companies. And the real question is how do we get there? And what is the process so far? So I want to give a little shout out to everybody here who is creating quantum hardware. People are doing it in different ways. There's a tremendous amount of science and engineering that has happened. There's a tremendous amount that has come. And everyone represented here, every company that's represented here has just done extraordinary work over the last few years to get us as far as we have. Now, at IBM Quantum, we put up the first quantum computer on the cloud. This was in 2016. In fact, on May 4th, we'll celebrate 5 years on the cloud. During that time, we've had over 320,000 registered users. And the number I find just mind-blowing is that if you look at the work that's actually been done on actual hardware, so this isn't simulators, this is real hardware. For those of you who don't know, the thing you send to a quantum computer and say, do this, we call it a circuit. And so people have run over 700 billion hardware circuits over those last 5 years. So people like to talk about quantum computing being a marathon. It's a marathon which we are now in the second half of the first decade of. So we've been going for quite some time here. The other extraordinary figure to me is that the usage of quantum computers has risen dramatically, as has the interest, as I think many of you will attest. People are running over 2 billion hardware circuits on our roughly 20 systems every single day. And that's in addition if they wish to use simulators. Now, who is using this? Well, it's really half and half, about half of all that usage is through the IBM Quantum Network, and these are the 145 members. You can see the industry partners. These are all people with whom we're working very closely on their particular areas of interest. They span financial, chemistry, Daimler is chemistry, batteries, for example, Accenture, Goldman Sachs, 3 different energy companies. The hubs, these are regional hubs. Some of them are universities. Some of them are Brookhaven National Lab is a hub. They reach out, they do work with other people in their region. Oak Ridge National Lab, which was mentioned earlier. The other United States Department of Energy labs work with them. Many members belong to hubs, dozens of startups, and dozens of universities. And we're interested in working with universities both to extend the research, right? Those key research that will be underlying a lot of the commercialization, but preparing the workforce of the future. which is critical. The people who are in university today are going to be the employees of tomorrow who have to have real experience with quantum computers, and it has to be part of their curriculum here. One particular client, IBM has worked with the Cleveland Clinic in many different ways. A couple of weeks ago, we announced a 10-year agreement with them, and it's very broad. It spans AI, other areas, but also quantum. All of our systems, the 20 systems, half of which are for the IBM Quantum Network people, the other half are wide open, and usage is about equal. But the Cleveland Clinic will be the first ones to get an on-premise quantum computer. We have started the planning for that, and they will also be getting, when it's available in 2023, one of the very first 1,000 plus qubit machines. So business models are evolving. Through the cloud today, yes. We can work together, yes. You can do it absolutely at no charge if you wish. And here we have example of yet this new type of arrangements, this new type of partnership to accelerate discovery in healthcare using quantum computers. We're not saying the results will come tomorrow, but you have to get started, and you have to be using the latest and the greatest quantum computers that are available. Now, how are they doing this? Well, they're doing it through tools, right? Right now, online, completely in the cloud, you can use the Composer, which is a drag and drop environment, or you can use the Quantum Lab. Quantum Lab is a Jupyter-based environment. Everything that is part of QuizKit, which is the leading open source software development environment, is available through the Quantum Lab. Now, I mentioned we have about 20 systems. Roughly half of those are open. You can go right now, in 5 minutes, you can be using an actual quantum computer, real hardware at no charge, one of the open machines. But we provide, I think, is unparalleled information about these systems and our progress. So it's one thing to talk about progress from a marketing perspective, because everyone wants awareness. Everybody wants to say, frankly, look, we're great, we're doing well, we're a player and things like this. But the proof is in the pudding. How well are your systems doing today, right? How advanced are they? We provide this type of information for every single one of our systems. A lot of this is technical information, but if you know what they are, such as T1, T2, some of these other things, you'll recognize what is going on here. In addition to the 20 systems, we have 5 simulators that are available at no charge. Not all quantum simulators are the same. Depending on the circuit you're trying to run, you can optimize it in different ways. These are all available. It's very easy to get access to simulators almost anywhere. I do want to emphasize, though, the future is quantum hardware, and the sooner you start your journey on real hardware versus just simulators, the faster your time to market will be. Now, this is the development roadmap, and this includes several different things. So let me hit a few points here. Roadmaps have to have certain things. They have to have years, all right? So that goes across the top. On the bottom is the hardware roadmap, and we first talked about that last September. So to quickly summarize, last year, 2020, we introduced the Hummingbird processor, and we name all our processors after birds. And we have somebody who can do wonderful little bird pictures too, as you can see here. This was 65 qubits. And so this Hummingbird device shows we can scale the number of qubits. But it's not just the number of qubits, right? It's the quality of the qubits. And this is measurements such as quantum volume. They go hand in hand. You increase the number of qubits, you increase the quantum volume. You go back and forth and back and forth. And this is how we'll get powerful enough systems with other techniques, right, to do this. I want to give a little shout out to Tony, by the way, the great work that Honeywell has done first in adopting quantum volume, but also the impressive results that they had recently. Now, later this year, we're going to introduce the Eagle processor. We don't believe you have to just glue together little chips. We believe that there's quite a bit of room to go in developing single chips that have many qubits on them for superconducting. Now, there's a lot of work that has to go through this. There's a lot of control work. Obviously, there's a lot of physics. There's a lot of engineering. Next year, 433 qubits. And then in 2023, the so-called Condor processor with 1121 qubits. I will leave it as an exercise as to where we come up with these weird numbers like 1121. Now, beyond this, we will be moving from chips, which as we can see get bigger and bigger. We will connect the chips. We will build quantum motherboards. We will connect quantum motherboards into larger fridges, as we call them, or super fridges. And then we can daisy chain those. And this is the path to modularization, right, to miniaturization, to ultimately get larger and larger and larger quantum systems, right, that can work together. And this is what will get us into the thousands and eventually into millions of qubits, which will allow us to support quantum error correction, fault tolerance, and things like this. So there are really three things that you should look for, right, as you're looking at systems. First is quality. How well are circuits implemented in the systems? This is where quantum volume comes into play. Capacity, how quickly can the circuits run on your systems? How much computation can you push through the systems to which you have access? Do you have access to a lot of systems? Can you do the work you have to do? And then variety. As I said earlier, this is not science for science sake. This is real practical computation. And so many of us have been working on this fusion of classical and quantum operations for years, because the idea is to have great results quickly, however we define that and for whatever use. So things like what we call dynamic circuits, right? Moving certain types of classical computations closer to the machine. Doesn't just mean sticking a standard classical machine very close. It's really understanding what parts of classical computation should be intertwined with the with the quantum calculation as well. This is a new type of interplay. It's not co-location of quantum and classical. It's actually full integration. And eventually this will mean full integration of quantum computers with what we now call high performance computers as well. So on the top here, it gives you a little bit more idea about what we're doing on the software side. So we have been demonstrating applications. All those people I mentioned early on, they have been working on this. This year through something called the QuizKit runtime, we'll be able to run our systems, well, we say 100 times faster, and I'll tell you, before we announced this, we were thinking 30 to 100 times faster. We've now shown, in fact, that we can do it 110 times faster than you can do previously. Dynamic circuits, again, bringing more of this classical type of processing to intertwine, integrate with what we're doing. Continuing to work in QuizKit to make it a great user development experience. That's really powerful. We will get larger and larger machines. We will be approaching error correction. All of this is an evolution. All different parts of the system, right, from the hardware to the software to the cloud support, will be evolving and working together to bring you the most powerful systems that you can use for the use cases that you have in mind here. So let me return just to QuizKit here. QuizKit is the most widely used open source software development environment for quantum. It's based on Python. It's had over 600,000 downloads. It's a great place to go to see, if you will, the breadth of what a quantum development environment should be. It's got hundreds of contributors to this, and I use it, I write about it. It's a quite powerful environment here. We announced last week that we are extending the very top layer. So it's one thing to be in the nuts and bolts and the gates and the circuits and everything of quantum, but what about the top layer, the part that users want to get access to? So we announced 2 new generations of our application modules, QuizKit Machine Learning and QuizKit Nature. Nature is related to chemistry, other physical processes as well. These join what we've already done around optimization and financial services. And oh, by the way, many of these techniques that are introduced in these particular areas are applicable across industries and to some other areas as well. Little QuizKit news. This came out yesterday. I'm very pleased that IonQ, not represented on this panel, but one of the leading providers for ion trap quantum computers, has announced full support for QuizKit. That means if you write using QuizKit, you can talk to our superconducting quantum computers, you can talk to the IonQ, ion trap computers, and there are also community supported backends. That's the part of QuizKit that talks to particular hardware available for a couple of other types of systems. So you do not lose the power of the underlying hardware by using something like QuizKit. That's the value of open source. This is what we've learned. This is what we've learned, for example, with Linux. Linux runs on many different types of hardware. We know how to do this today. And so writing great software, writing great software development tool chains is really critical to get us to the point of really solving actual use cases of what we're trying to do here. I want to end with an invitation. 40 years ago, in 1981, was the famous IBM MIT conference. And this is the one where Richard Feynman, ultimately in his paper, from the conference, he said that nature isn't classical, damn it. And so what he meant was that if we're going to be working with nature, doing things like with chemistry and physics and biochemistry, you'd better come up with a computer that is based on the same principles, by which he meant quantum mechanics. We are holding a virtual 40-year anniversary. It is open to everybody. I hope you can join us. Several people, such as Peter Shore, Steve Gervin will be with us. Toffoli will be there as well. We have invited speakers. I think it's a great way to punctuate how much progress we've made so far, and also where we're going to go. So with that, Amit, thank you very much.
Thank you, Bob. Fascinating overview and insight into the IBM roadmap. We look forward to seeing those developments come to fruition. Next up, we have Tony Uttley. Tony leads Honeywell Quantum Solutions and is responsible for the strategy and business execution of Honeywell's unique technical capabilities in the field of quantum information systems. Tony, the floor is yours.
Thank you. It's great to be here. I actually want to start the same, at least similar to how Bob started his, with a bit of a shout out to those companies around the world that are working on quantum hardware. You know, I think it's amazing to me to see the progress that has happened over this last year, considering what has happened this last year. You know, as you might imagine, you don't go build a quantum computer in your house. That's not how it works. And so the women and men around the world who have had to go in every day to try to make this world-changing technology happen have been incredible and have been absolutely outstanding. And that's something I certainly have been super proud of the Honeywell team, but really of any of these companies around the quantum computing ecosystem who are trying to push the boundaries on what's possible for quantum computing. It is actually terrifically amazing to me to think about what has happened over just that past year. So almost a year ago, just over, we announced that we were going to be releasing our first commercial quantum computer. And we made a bold statement that said when we released it, it was going to have a quantum volume of 64. And then we said we were going to be able to improve that quantum volume by an order of magnitude, right? A factor of 10 every year for the next 5 years. And I know when we did that, first, many people didn't even know Honeywell was in quantum computing. And then there was at least equally amounts of people who thought there's no way you can make claims like that and back them up. And so very proud of the, of the team, because we got hit by a pandemic immediately following that statement. And yet in that same timeline, so within 3 months, we did release our first commercial system, our system model H0. It did have a quantum volume of 64, and we have continued to make exceptional progress. So how did we do that? Right, this is underpinning a decade of Honeywell focusing on quantum computing. And while we were purposefully not real vocal about it, the reason we were able to go do it is because many of the things necessary to go build a quantum computer, any quantum computer, are things that Honeywell has done for decades. And that's things like cryogenic systems, ultra-high vacuum systems, in our case, lasers and photonic systems. We build our own traps in our own trusted foundry. We make our own bespoke control systems that come from the underpinnings of our aerospace business and our satellite business. These were things that we had a generation of technology to be able to rely on and then put together in a way that for us, and we all have technical debt here to be able to overcome as we scale up these systems. We took a lot of our technical debt early, and we did it in a way that we believed we could then come in and rapidly scale our quantum computers and make them available then to our partners and to our customers. We relied on a underlying technology of trapped ion quantum computing that, in the architecture approach we use, allows us to get to extremely high fidelities. So, this view of 99.5 2-qubit gate fidelity is what we promise at a minimum on our H1-1 system. We're typically running in like the 99.7, 99.8 range. For our single qubit, again, our 99.97, we typically run at 9 times 10 to the minus 5. Our SPAM, our service state preparation and measurement, again, they do not become the limiting errors. Our limiting errors actually are our 2-qubit gate errors, and allows us to do things when you have a fully connected set of qubits with this type of a profile that are genuinely hard to go do, which is why we're able to increase this quantum volume so quickly. It also puts us in a position to continue that progress rapidly. So we have 2 commercial systems available today. We have one that we call our system model H0, and we have one that's our system model H1. Our system model H1, we purposefully released at less than 0.01% of its full capability. Less than 0.01% of its full capability. So why would we do something like that? Because we were being asked to do it by our customers and our partners. They wanted to have access to the system right now. And so we actually built a model around what our customers were asking us for. It turns out that most people don't want a minute or 5 minutes of quantum computer. They want hours and hours of quantum computing. Why? Because that's how you make progress. That is how you make rapid progress on the algorithms that are going to be useful in the near term. In fact, just this week, after a long time waiting, I have to say, it takes a little while to go through the journal Nature process here, but we had our paper published on our quantum charge coupled device architecture. And really in that, we demonstrate how we are able to do what we are able to do in terms of scaling as quickly as we are. We also talked about some recent events that we've had with some of our partners, and that is Honeywell has been focused on quantum computing because we are in businesses that we know are going to be profoundly impacted by quantum computing. The aerospace industry, our chemicals business, our process controls business, these are going to be profoundly impacted. And our belief a decade ago was you either let that evolution happen and then figure out how you change your business model, or you help shape how it evolves. And so we took that approach. We were going to be our own biggest customers. In fact, we do work right now in both chemistry and optimization for internal use cases that are going to help shape how Honeywell evolves its offerings. But we had some great partnership interactions with Cambridge Quantum Computing and DHL, looking at what they call these unit load device, how you put together packages more efficiently, with Samsung and Imperial College London, looking at spin models, particularly examining magnetism for use in future batteries. We had a fabulous work with BMW and Entropic Labs that was looking at machine learning algorithms that would be recursive QAOA for future logistics needs. And with Merck and Zapata Computing, again, looking at machine learning, and again, looking at logistics, because there are many more types of optimization problems in that part of actually the entire pharmaceutical value chain that are going to be potentially useful in the near term. And the key for us is always focus on where value creation can come from. It's not to say that these are doing something today that you can't do classically. Much the opposite. This is the critical time in quantum computing where you're able to understand what the answer absolutely is and then validate it that you can get the same answer off of these quantum computers. Because we are going to cross that boundary and we're going to do it soon. And when we do it, you have to have taken the opportunity to build that trust. We made our roadmap public late last year. And just to give a little bit of a further voiceover on it, these are systems that were designed to be able to scale. So we built our entire evolution of our business around our system model H5. You can almost think of every model before it as a development system critical for delivery of H5. And as you start with system model H1, you say, okay, well, I know that's in the market now. I know people are using it today. Are there evidence that would suggest that we have the ability to go demonstrate? The answer is yes. System model H2 is physically built. It sits right next to system model H1. We're already doing the trapping and the integration activities. System model H3, it looks fairly different. We're starting to have some two-dimensional geometry there. So the first question is, are you going to be able to turn corners with your qubits? And so the picture below is the trap that we use right now to demonstrate that we absolutely can do junction transport, take 90-degree turns. And then you integrate photonics, and then you start to talk about tiling these together to scale. We built our entire organization around a premise that once you get past the physics, which is substantial, it becomes both an engineering problem and, importantly, a controls problem. Doing quantum computing at scale is a controls problem. And fortunately, we are controls experts. We have been able to put together not just mid-circuit measurement and qubit reuse, but also things like conditional logic, so that you can take advantage of writing in your algorithms approaches to being able to understand what is that qubit right now in the middle of this circuit. Are you a 1 or are you a 0? And build in logic that says if you are a 1 versus the other, then you're going to do something different. Why can we do that? Two things. We have very long coherence times, so in the 3 seconds range, and we have the ability to control precisely what our qubits are doing. And it really comes to this quantum charge coupled device architecture, which is we are physically moving our qubits around to be able to both have them interact and also separate them enough where you can measure them and interact with them in the future. We are extremely pleased with the progress that our systems have demonstrated already, but also the technology roadmap is underpinned by these critical milestones that we've already demonstrated, and that gives us substantial confidence that this is going to be a fun decade. The last piece I'll leave before I go into maybe even some time for question is to go into error correction. You need to be able to do some of these things. You need to be able to do mid-circuit measurement. You need to be able to do conditional logic. You also need to be able to do something called syndrome extraction, which is in real time, measure what's going on, measure what the error is, and correct for the error during the middle of the circuit. Those are called rounds of syndrome extraction. And we have presented recently that we are able to go do those multiple rounds of syndrome extraction in our systems today. So when you see that shading of moving from this NISQ era into this fault-tolerant quantum computing, it's not just where that in PowerPoint would have laid out. It really is something that we're confident that we're going to be able to get there fast. So I will pause there and say we are excited to have additional customers and partners. We've actually been fully subscribed on our systems to date. but we're bringing another system online here in a matter of just a few weeks, and we'll expand out the capacity and bring new partners and customers online.
Thank you, Tony. It's fascinating how you're leveraging your engineering and controls expertise and applying it to this domain. You do have time for a quick question around software. You're a hardware player, and for a quantum hardware player in the long term, how important do you think will it be to have a software capability in-house, or can partners bring this in?
So we're using some of both. So we do have a full stack. We have customers who we just supply an API key and they're able to go do the rest. We use OpenChasm as the entry point, but we have fabulous partnerships with Cambridge Quantum Computing using Ticket, with Zapata Computing using Orchestra. You can use Qiskit and be able to link in. And then we have a relationship with Microsoft Azure where you can use their Q# software to come in through that venue as well. It's going to be let's call it a harmonization of capabilities over time. And it really comes down to finding those near-term value creating applications and then making sure you can take it all the way from the proof to operationalizing it. And that's why Honeywell is so excited about this. That is what we do. We go and operationalize the ability to take computation through to a new chemical plant, or all the way through to a new warehouse optimization scheme. So that's really exciting for us.
Wonderful. Thank you very much, Tony.
My pleasure.
We will move on now to Zachary Vernon. Zach is the head of hardware at Xanadu, where he leads a team of about 30 physicists and engineers building the world's first photonic quantum computers. Zachary has a PhD in physics from the University of Toronto and has expertise in integrated photonic technologies for generation, control, and measurement of quantum light. Over to you, Zach.
Well, thanks very much, Amit. Can you see my screen okay? Somebody has to say yes. I can't actually see. Great. Okay.
Yes, we can see it.
So thanks very much for the introduction, Amit. I'm very pleased to be here. Thanks for the opportunity to speak. I'll be telling you about our efforts towards scaling and building photonic quantum computers. A bit about us first. So we are a full stack quantum computing company. So we're working on both hardware and software. Our hardware is based on the photonic approach, where we use photonics essentially for every part of the stack. So as opposed to just using it for certain elements in control, as you would, for example, see in trapped ions, we also use it to actually process the quantum information. We have a full stack platform, as I mentioned. We access directly, we offer access to our hardware directly with Strawberry Fields package, but we also have a software offering, which is hardware agnostic, and that's Penny Lane, and I'll speak a bit more about that in a few slides. A fantastic team, over 70 people. We're based in downtown Toronto, Canada, offices and labs on the upper floor of an office tower where it's we get to build quantum computers with a view, which I think is a nice, unique aspect of where we work. So often get asked, if photonics, say 5 or 10 years ago, was sort of the wrong choice for quantum computing, and it probably was, and therefore the bets being placed on the other approaches at that time were probably the best bets to be, best ways to make those bets. What's changed, right? Why now? What about photonics makes it ready for prime time and ready for a very demanding application, which is quantum computing? And I think it makes sense to split that into two areas. There's the innovations that we can take credit for at Xanadu, but then perhaps as important, there's the innovations that are given to us for free by the broader maturation of the optical telecom industry. This is an industry that we have a synergy with and that we can borrow a lot of tools from, that we don't therefore have to develop all ourselves. In terms of things that we can take credit for, a big game changer for photonics was the demonstration of a squeezed qubit in an integrated platform. A squeezed qubit is a different kind of qubit. It contains many excitations, many particles, if you want. In a sense, you can think of it like a multi-photon qubit. And that allows you to unlock very different encoding schemes and, crucially, a different path to fault tolerance and error correction. And this had been around since the 1980s, but no one had ever demonstrated a chip-integrated version, which is necessary for scaling. So we came on the scene, and that was sort of the hardware team's first goal, was developing this chip-integrated version of the qubit. We also have a lot of innovation around photon detection in partnership with NIST in Colorado. And we have published a blueprint for our path to fault tolerance. I think really one of the only companies or approaches to really put our money where our mouth is and lay out in detail how we will achieve error correction, full fault tolerance, and universality as we go forward. So that blueprint is available for anyone to read, and gives us a kind of mandate to carry for the next 5 years and develop. So obviously innovating is fun and important, but it's also very expensive and time consuming. So we don't want to have to invent everything ourselves. And that's where we benefit very strongly from a synergy with the optical telecom industry. Photonics is the platform of choice for communication for good reason. And that billions that have been invested in that industry have given us things like the laser, telecom lasers, matured the industry that's involved in actually manufacturing chips for photonics. This is something that has been around for a while, but in terms of performance and capabilities, the quality of that fabrication, only in the past 3 to 5 years has that actually emerged and been able to meet the demanding requirements of quantum circuits. And then there's just the fiber optics themselves, fiber optics and the fiber optic components. You know, we didn't have to invest billions in developing these things that allow us to connect our chips and exchange quantum information and modularize and network our quantum computers. Corning and Sumitomo have spent the past 40, 50 years doing that for us. And we get to borrow a lot from those technologies as well. So not having to reinvent a lot of wheels allows us to progress faster and also in a more cost-effective way. So this kind of shows end-to-end what we do on the hardware side. And that's really every element of the stack involved in quantum hardware, except for chip fabrication. And we work with the world's best foundries to prototype our chips. So we work on chip design ourselves. We then send those designs off to the foundries that we work very closely with those foundries to the point where we're talking directly to process engineers and clean room technicians. So it's sort of the next best thing to having one's own fab. We test and characterize all of our chips in-house, and then we put it all together and package them and deploy them for cloud access and iterate. We've been through about 8 QPU generations, putting various chips online, over 15 foundry cycles. And as I mentioned, we have it all really happens in one lab in downtown Toronto. And we have 7 quantum computers so far that we've built and made access available to. So I'd like to take a moment to talk in a bit more detail about one of those machines, one of those quantum computers that we've built and made available to everyone for cloud access. And that was our first one. We call it the X8 chip. It's an 8-qubit quantum computer, photonic quantum computer. It's sort of was our flagship chip that we emerged kind of out of stealth with and made available to the public. It's been running for just about almost 2 years now, nonstop. We kind of call it Old Faithful, this particular chip, since it was our first, and really has been going uninterrupted since then. It's a very unique device that's based on squeezed qubits and something called a programmable interferometer. These are the gates that the user actually loads, and they're compiled. The quantum program ends up being encoded into as a series of analog voltages in this interferometer. This science that went into this at the early days of our company was groundbreaking in its own right. The squeezed light sources themselves, you can see they made the cover of Science Advances. So sort of a real breakthrough in qubit generation technology. And the full systems description of this device was recently published in Nature, just actually a couple months ago. So you can read much more about this particular chip and all the applications that you can apply, use it and embed with this chip in that paper. So, pardon me. So when you put all that together, what does it get you, right? What's the actual value proposition of photonics as a hardware platform? And in terms of the benefits that photonics give you, as in contrast to the other approaches, I'd split it into 4 areas. We have the blueprint to 1 million qubits. So scaling to 1 million qubits has been investigated and laid out in detail, the pathway to get there in a much more comprehensive manner than any other approach. And that all boils down to the networkability of our chips. Because we're encoding information with light and communicating quantum information using light, using fiber optics is straightforward. It's in fact almost trivial. Don't really have to do anything too special. It is much easier for photonics to distribute those million qubits that we're all after onto many chips and then connect them. And this is a real bottleneck that's being faced by all the other approaches, where just even 2 chips sitting next to each other in the same room, in the same lab, really have no reliable way of exchanging quantum information in qubits back and forth. So there will come a time when you're going to need to split up your qubits. Maybe it's at a level of 10, 30, 100,000. I can say with confidence that 1,000,000 qubits won't all be in the same quantum module, right? You will have to distribute that. And then you're going to have to be able to network them. And that's where fiber optics comes in. And really only photonics has this advantage, being able to do this not only photonically and optically, but actually using telecom wavelengths, using the same wavelengths of light that are already facilitating this digital conference, right? We can develop faster, and that really relates to our room temperature aspect. Also, there's no vacuum required, very benign environmental conditions for the actual chips that do our computation. And that just lets us iterate much faster. This room temperature aspect does also allow you to imagine in the very long term a wider deployment context of these devices closer to the edge. But for engineers, in the short term, that just means we don't have to cool our chips down to the temperature of outer space or colder, and then bring them back up to room temperature just to characterize one chip, right? That can happen in minutes at the wafer scale at room temperature with no vacuum either. Manufacturability is key. If you're going to get to 1,000,000 qubits and they're going to be distributed on hundreds or thousands of chips, you need to be able to use a foundry that can manufacture at that scale. And that's where photonics really shines, because it can take advantage of the most modern CMOS foundries, right? We don't have to work with nearly the same degree of specialized and exotic materials and processes, so we can plug directly into fabs that are already producing photonic chips at volume, right? And so when it does come time to scale up even further and actually go to production, we can plug directly into the likes of TSMC, Global Foundries, or even Intel now has spun out their own dedicated fab offering. So it plugs directly into those. Whereas I think a lot of the other approaches are going to have to contend in the long term with building their own fabs. And that's going to be very costly and time consuming as well. Last point I'd say is less widely appreciated, but very important. And that's that photonics is actually faster. And I mean that literally. The clock speeds of our QPUs are already about 1,000 times faster than competing approaches. And this is really one of the reasons, again, that photonics is so good for communication. It has an immense bandwidth that allows you to modulate and encode information at extremely high speeds. So we're already operating about orders of magnitude faster than the other approaches, around megahertz. And we can actually continuously improve all the way up to several gigahertz, more being limited by the availability of classical coprocessors at that point. And where the other approaches are going to always be bottlenecked at this slow, kind of more kilohertz to low megahertz kind of clock speed domain. So if you imagine a world, say in 10 years, we're all successful, we all have 1,000,000 qubits, fully fault tolerant. Photonics, in a sense, still has an advantage, just because it can actually attain a much, much shorter time per clock cycle, per gate, per operation, much faster reset times as well. There's no relaxation you have to wait for in the underlying qubits. We're scaling very quickly, right? We do move fast. I think considering the context of the field and how when we started, we're really at par now with the cutting edge. So we have a 40 qubit chip, just came back around over Christmas last year, and it's being tested right now, roughly doubling our qubit counts on chip. You can see in these photos, these are our actual devices. As the chip gets larger and the control, of course, becomes more complex, it gets a bit more difficult, but still scaling very, very quickly and continuing, we believe, to be able to meet this doubling every 6-month pace when averaged over a few years. So we're well on our way to thousands of qubits in the next few years. And I think no other approach can really claim that rapidity of scaling, especially considering that we just integrated the first one of our qubits on chip only in 2019. So quite a rapid, or 2018, quite a rapid pace. We have a very clear path to fault tolerance. As I mentioned, we've made this available online. If you'd like, you can find it on I think it was published in Quantum. This is our way to correct for errors necessary in any quantum platform. And it relies on something called GKP qubits. This is a different type of qubit. It has more than one energy level. You can think of it like that, or it's composed of qubits of many photons, so more than one possible state. And it is the leading candidate for photonic quantum computation. You essentially embed information in these qubits, and these qubits give you an intrinsic robustness to errors. And that's because the dominant source of error for photonics is losing a photon. And if you lose a photon from a GKP qubit, the qubit is not destroyed, it's not deleted. And that gives you an intrinsic resistance against the dominant pathway for errors. The chips that I described, the X8 chip that I showed a picture of just a few slides ago, in fact, that is the fundamental building block for synthesizing these GKP qubits. You use these, you make many copies, and you harvest these GKP qubits You knit them together into a three-dimensional cluster state shown here on the right. And all of this, of course, comes down to squeezing. And one of the key aspects of this is that we can implement error correction also in a very benign environment at room temperature on a standard circuit board sitting on one's desk. Right, that cycle of feed forward that was just described in the previous talk, where you have to measure from the quantum domain, do some classical computation, and then correct an error by feeding forward. That all happens for us on a standard circuit board, and that's extremely powerful since error correction is going to be so critical going forward. As I mentioned, we're full stack. So at the very bottom of everything is our hardware layer. We have our quantum processors. As you move up, I won't go through everything in between, but we also have some software offerings, which I should say, Strawberry Fields is how you program our photonic quantum computers. And then Penny Lane, much more generally, is rapidly being adopted as the dominant platform for quantum computing. It started off as a quantum machine learning library, but it's now really expanded much beyond that, and is really taking off with a very large amount of engagement, and in between a bunch of managed services that we've also made available to customers and are seeing a lot of traction with. A bit more about Penny Lane. We have, as I mentioned, it's hardware agnostic, so it's nothing to do with photonics. It can plug into all the other platforms. We do have plugins for all the dominant hardware platforms and approaches. We're partnering with AWS to co-develop this. And as I mentioned, it's rapidly becoming, I would say, the dominant platform for this. We had our developer conference a couple months ago, and it had thousands of attendees. So really, really rapid progress and adoption on this, which we're very happy to see. And it's, of course, open source and free, so anybody can use it. As I mentioned, a world-class team, over 70 people, and we're really starting to pull now from the best institutions, both academically. We have people from MIT, Stanford, Harvard, Berkeley, the like, and now also from industry, recruiting from foundries, major foundries, and other real top tier 1 tech companies that are all moving to Toronto to join us in building the world's first photonic quantum computers. I'll leave it there. Thank you again, Amit, for hosting me, and thanks for your attention.
Thank you so much, Zach. Going to be fascinated to see the progress on the roadmap over the coming years. Well done so far. Moving on, I'd like to introduce DV, David Vettese at Alpine Quantum Technologies, better known as AQT. DV's role encompasses the sales and marketing of trapped ion solutions, from individual linear Paul traps to full quantum computers. Prior to AQT, he was in senior commercial roles at Scottish photonics companies, including spatial light modulator manufacturers and a leading laser provider to quantum technology experiments. Over to you, DV.
Thanks very much, Amit. Let me just get this sorted out. Can you see my slides? Can I just check you see the slides? Okay.
Yes, all good.
Grand. Well, thank you very much for hosting such an excellent event. Very much enjoyed it thus far. So good afternoon to everybody who's attending. Thanks for attending. As Amit's pointed out, I'm DV, David Vettese. I'm part of the sales team at AQT GmbH. So my talk this afternoon, which is Quantum Computing Commercialization Path, perfectly titled to describe the journey that I've been on as part of AQT and how that relates to our customer base. Commercialization is essentially the process of managing or running something principally for financial gain. And well, we run a quantum computer company specifically for revenue and profit generation. I'm going to tell you how we do that. No secrets here. I won't cover the why we're walking down this commercialization path. The why is covered in many talks by other colleagues, other companies, other vendors. But let's just say, we are a trapped ion product manufacturer that is in a position to address a global market demand for quantum hardware. And we're working towards bringing our solutions, a series of solutions to the market. Anyway, not much time, so we better move on. So just in case you haven't heard of AQT or you're missing a couple of bits of information, I thought I'd start with a little introduction to the company. As per the title of the talk, well, where are we? Well, we're in Austria. My accent is Scottish, but the team are based out of Austria. AQT are in Innsbruck, which is in the beautiful part of Austria called the Tyrol. Our main premises are sited just at the foot of the mountains in the university campus of the University of Innsbruck. This is a very successful physics university with a lot of brilliant cold atom, trapped ion, quantum emitter research groups, amongst other brilliant academic fields. Indeed, we spun out of the University of Innsbruck in 2018. We're founded by three excellent, exemplary scientists from the university, Professor Rainer Blatt, Professor Pete Zoller, and Dr. Thomas Mons. So you'll know Professor Blatt is one of the experimental physicists, has his own team there, and Professor Zoller is widely regarded as having first theorized the concept of using trapped ions as a qubit for quantum computing. And Professor Blatt's team as the experimental team worked very close in collaboration with Professor Zoller's team, and were able to do a show initially the entanglement of a number of ions, qubits, and have held the record for the number of entangled ions since that initial finding. The third founder is our Chief Executive Officer, Dr. Thomas Mons, an award-winning experimental physicist, an exemplary industrial experience, which was done with myself in the Scottish company. And much of its time has been spent as the senior scientist in Professor Blatt's team, but now he holds a position of Chief Executive Officer. So we've grown and evolved since our founding 3 years ago, and we're now a team of 20 scientists and engineers based on the university campus over a couple of sites there. Our seed funding supported by the Federation of Austrian Industries Tyrol, the FFG Austrian Research Promotion Agency, and of course the Institute, I beg your pardon, the University of Innsbruck is in excess of 10 million euros. We already have an existing and expanding customer base for our trapped ion products. We've shipped and installed some of our linear Paul traps across 3 continents to date. We're always looking to assist new customers, and we'll discuss that later. Since founding, we've also looked to build partnerships and alliances with complementary companies who offer products and services which enable faster adoption of quantum computing technologies. We have more than half a dozen of these key strategic partnerships, and we look forward to working with many more in the near future. So we may differ in our approach from some of the larger companies, and some of the larger companies have spoken today and other talks. And we also probably match the ambitions of a number of other smaller startups. But we all look at revenue streams that are coming in, say, 5 to 10 years' time from a thriving quantum ecosystem, which is packed with everyday uses of quantum computing and everyday applications of quantum computing. But we're told about this almost daily, you know, from journalists and from analysts who herald the arrival of quantum computing. And by those that are maybe a little bit skeptical that the funding, I beg your pardon, the revenue that can be generated isn't going to come for another few years. Well, actually, AQT are about generating revenue now. In some senses, our path has led to today when we're making money today. And maybe others expect cash to come in a little bit in the future. That's not us. So let me tell you how we do it. So when we talk about AQT and the commercialization paths, we essentially talk about 2 very distinct product offerings, which have a few configurations, which will be available to our growing customer base. We have the quantum computing modules products, and we have the quantum computing system product lines. For the quantum computing modules, I've already mentioned that we have an existing base of customers that are taking our trapped ion products, for example. These research accelerating and application seeding modules will enable new quantum developments via immediately availability of exemplary trapped ion products such as linear Paul traps and optical references. This way, we're enabling the growth of a future quantum ecosystem. And in the 5 to 10 years' time, when we've seeded a few more quantum trees, when we've, when we've got new trails that are defined, or even, new peaks that have been conquered by trapped ion quantum computers, you'll come back and thank the team from the Alps. But what if your desire is to work on quantum computing today, you haven't got time to manufacture your own trapped ion device, and you want to have something straight out of the box? Well, we've got some European-based solutions in place for you right now. We can offer a quantum computing paradigm to meet the way of your working. We can offer access to our quantum computing backends over the cloud with the quantum hardware residing here in Europe. We've got multiple devices to meet the demand and can offer access now to our closest partners. Further, and something that's taken quite a lot of my time up considerably recently, we can offer the quantum hardware on premises. This has a number of benefits over, say, cloud solutions, as it offers exclusive and secure operation within a customer's location, or indeed within the confines and security of a leading data center. This is available in a hardware as a service model, or in a strangely traditional manner, you can purchase a unit outright from us. Please do feel free to get in contact with me if you want to organize to get a quotation for a quantum computer. That's why we've got the team in place for it. So as I mentioned, the quantum computing modules are a series of ion traps, optical references, and other accessories for predominantly quantum information applications, but could easily be used for a range of other quantum technology applications, such as quantum clocks, ion clocks, or indeed for quantum sensors. The linear Paul trap at the heart of our quantum computing processor, for example, we call it the Pine trap, is available as a standalone item as per the lower left-hand image, or within a larger assembly with vacuum and optical components as seen in the images as you go towards the right-hand side. Each are larger assemblies that incorporate the gold-plated 3D Paul trap, and every level of assembly that we offer will depend on the customer's requirements and, of course, the budget. Another of our products, which is not shown here, is the Birch optical reference system, which is for locking and stabilizing lasers, such as for laser cooling, ionization, and repumping of your ion trap laser lines. It's worth noting these assemblies are the exact paradigms that we use ourselves within our own quantum computers. All our products are provided along with a number of key documents and product-related collateral, such as user warranties and user manuals and warranties. We can provide products with a rapid lead time as well. So none of this is really groundbreaking stuff, but it genuinely enables new quantum developments and new quantum applications. Our academic heritage has made us consider that this large market it should be supported, and our ion trappers in place at AQT are happy and motivated to work with new customers to enable the installation and use of these innovative trapped ion products. So one of our first customers, and indeed our closest customer in Innsbruck, is the Action Consortium. Action Consortium is a major research project funded by the European Quantum Technology Flagship. It aims to develop and exploit a robust and compact ion-trap quantum computer based on scalable quantum hardware and widespread industry standards. Project partners, including the University of Innsbruck, of course, Toptica, Atos, ETH Zurich, amongst others, have all contributed to the development and realization of a compact ion-trap quantum computing solution. At the heart of this demonstrator lies one of the AQT trapped ion products. In particular, the beating heart of this is, or maybe even you maybe want to call it the blinking eyes of the quantum computer, is that ion trap that we've provided, the 3D linear Paul trap, the Pine trap. The Action team have eloquently and succinctly detailed the process of building the quantum computer. Essentially, in my mind, you've got a blueprint there for a high-performance trapped ion quantum computer in that archive submission that I've listed there at the bottom of the screen. Speaking to Dr. Thomas Felker, one of the team in the Action team of University of Innsbruck and Professor Blatt's team, he was delighted to recount the almost instant success that was achieved by the system that was developed in Innsbruck, which utilized the AQT products. So, and here's just some of the numbers. I think you'd probably be very interested in this. There's probably a few photographs being taken at this point in time of these specifications. Through a lot of hard work and brilliance by the Action team, they're able to achieve what is known as the world-leading Greenberger-Horn-Zeilinger states with up to 24 ions without the use of post-selection or error mitigation techniques. We're absolutely delighted to work with many customers to enable them to also achieve these world record results. At the same time, the action demonstrator that we see here can now be added to the European quantum hardware resource pool to enable further validation of quantum algorithms and work with new ideas. That very quantum ecosystem that I spoke about earlier is richer now for the efforts of the action team that are using some of the AQT products. So what is the status and the capabilities of the AQT quantum hardware? We've enabled others, but what have we actually done ourselves? That's a good question. Well, we've been designing and building our trapped ion quantum computers to be available now on the cloud or as the on-premises, as I mentioned earlier. The on-premises installation, akin to the units that we've got installed at AQT HQ in Innsbruck, have been built to be housed in these two 19-inch rack systems, which have featured once or twice within the presentation. It's going to operate happily in the environment of the data center. So you can accommodate, we can work within standard vibration and temperature conditions. As the ion trap operates at room temperature, we have no cryogenic systems required. And indeed, there's absolutely no water cooling inside these cabinets. It's air cooled throughout. The reason for that, it's low power consumption. The power consumption of the entire unit is about 3 kilowatts, and it can actually operate in a single power plug. But I think given the investment you're going to be putting into quantum computing, that's going to be the last of your problems. So we have a few units which are at varying stages of completion, which are named after the local flora and fauna within the Alps region. The Ibex, for example, that's our first unit. It's available now, excuse me. That's available now, excuse me, and is currently running some algorithms for some of our partners. The Pine is our freshest ion trap system and will be online soon after we complete work on the Ibex. Both exhibit significant performance, so we can address up to 50 qubits with each unit, and with the 2 gate Moore Sorensen setup, we can expect to achieve gate fidelities in excess of 99%. As with all trapped ion systems, we're going to achieve all-to-all qubit connectivity. However, please note that these are not the full capabilities, and these are not the definitive pieces of information. Both systems are currently being characterized to give official numbers in the product specifications. Our preference is to maintain the behavior of submitting our measurements and capabilities through peer-reviewed and scrutinized scientific publications. So keep an eye out in the archive or through leading publications, and then subsequently on our social media platforms for definitive information relating to our quantum computers. We're often asked as well, can we present a roadmap? Sadly, today, I won't be furnishing you with a graph or a positive picture to portray the future. Simply, we'll state we'll build what the customers ask of us, and not something that nobody needs. Our most recent communication with key customers and partners across multiple industries have called for only the 40 or 50 qubits, and we'll be pushing those towards fault-tolerant performance levels and build them to be operated in environments which are running 24 hours a day, 7 days a week. If you disagree with my roadmap, please do get in contact. Let's build to what we actually need. So briefly, before I finish, I couldn't escape the fact to tell you that AQT are always recruiting. In particular, Innsbruck is stunning. It's absolutely beautiful. If you love your skiing, if you love your mountain climbing, if you love your hill walking, Innsbruck is a place to come and be. We'd be keen to speak to anybody that's interested in pursuing a career in quantum computing that would like to work for a hardworking and sociable team. Please do get in contact if you have the skills and you believe your ambitions are going to match your own. So that's how we plan to commercialize. We've got the information there for you. We have routes to revenue generation with our multiple product lines, and indeed, we're making money now. The quantum computing modules, the ion traps, references, the exact paradigms we use ourselves, being sold across the globe, enabling new and exciting applications and experiments. Quantum computing systems, we offer also available now, available via the cloud or by on-premises. There are other purchasing options. Let me know. Overall, we're going to be delivering a credible trapped ion product that meets requirements of the customer base that we've spoken with. We're here to assist, and we'd be delighted to do so. Thanks.
Thank you, DV. An excellent overview. And to conclude, I'd like to thank all of the speakers today. Whatever the architecture, whatever the approach, it's such a fascinating roadmap, and we're all excited to see what comes over the next year or two. Really appreciate all of your time, and well done for the progress that you've made over this last year. So thank you all very much. Audience, I apologize there wasn't enough time for questions there. It was pretty fast moving. Please do get in touch with the speakers individually on the platform, and please do look forward to the lunch and learns, which are just about to get underway after this session. Thank you all very much.
Thanks, Emmett. Bye-bye.